Lesson 6.1, linear versus exponential growth. Our objective for this lesson is to be able to determine whether growth or decay is linear or exponential and calculate the quantity at the end of a given time period. So we need to start by defining linear and exponential growth and decay. So linear growth occurs when a quantity increases by the same amount in each unit of time. So when we say the same amount, we mean the same absolute amount, not a percentage, but the same absolute amount. And it's increasing by that amount every month or every year, every day. An example of linear growth would be I add 2 YouTube videos to my account each week. So the total number of YouTube videos that I have is increasing by 2 per week. So that's an example of linear growth. Linear decay occurs when a quantity decreases by the same amount in each unit of time. So for example, if I have a 12-pack of soda and I drink 1 per day, then the total quantity of soda that I have left is decreasing by 1 per day. And that's an example of linear decay. Next, exponential growth occurs when a quantity increases by the same rate in each unit of time. So instead of increasing by the same absolute amount, it's now increasing by the same rate or the same percentage. And we saw lots of examples of exponential growth in the last unit on money. For example, compound interest is an example of exponential growth because the amount of money that you have in the bank is increasing by, say, 5% per year. And so that's going to be more and more absolute amount of dollars that's coming into your bank account each year. It's increasing by the same rate, 5%, but that's more and more money each year. Exponential decay occurs when a quantity decreases by the same rate in each unit of time. So an example of exponential decay would be the depreciation in the value of a car, for example. Your car's value is going down over time as you drive it, and it becomes less and less reliable. But it's usually the value is going down by the same percentage each year. So say the value of your car is depreciating by 10% per year. It's going to lose a lot of value in that first year, and every year after that it's going to lose less and less of its value because it's decreasing by 10% of its value at the beginning of that time period. Our first example says the number of students at Williamsfield High School has increased by 75 in each of the past 4 years. If the student population 4 years ago was 1,800 students, what is it today? So here we have a chart, and we have Williamsfield High School. We're adding 75 students per year, and we started with 1,800 students. And so after 1 year, we're going to have added 75 students to that population. So that's going to be 1,875. The next year, we'll add another 75 students. So that's going to bring us to 1,950. After the third year, we're going to have added another 75 students. So we're adding 75 to this number now, and that's going to give us 2,025. And then we'll add another 75 students. So that's going to bring us to 2,100 students, just adding 75 students per year. Now, the second example says that the number of students at Higley High School has increased by 3% in each of the past 4 years. If the student population 4 years ago was 1,800, what is it today? So now we're increasing by the same percent each year rather than the same absolute amount. So what we have to do is take this 1,800 and multiply by 3% or 0.03. And that's going to tell us that after 1 year, we're going to have added 54 students. So that's going to be 1,854. Then we're going to add another 3% to that. But now that's 3% of 1854. And so in the second year, we're going to add about 56 students. So we're going to round to the nearest student so that we're not talking about portions of a student. So that's going to add another 56 students approximately. So that's going to bring us up to 1,910 students after 2 years. And then we multiply this 1,910 by 0.03. That's going to give us about 57 additional students, bringing us up to 1,967. And then if we multiply 1967 times 0.03, that's going to give us an additional about 59 students. So that's going to bring us up to 2,026 students. So I did these two examples together just to show you a couple of things. One is this Williams field growth is an example of linear growth. We're adding the same amount each year. Higley is an example of exponential growth. We're adding the same rate each year. And there's often a misconception that exponential means a lot. So exponential growth means we're growing a lot compared to linear growth. But you can see here that Williams Field's linear growth has led to a larger increase over 4 years than Higley's exponential growth. So what I want to ask you is this, and I'll leave you with this question, is which school is going to have more students after 10 years? Which school will have more students after 20 years? Those are the types of questions that we're going to be answering in this unit as we learn to model with linear and exponential growth and decay.